The extended Euclidean algorithm for a lot of us at first can be a little bit daunting because there's a lot of stuff to keep track of. And knowing and remembering which values we're keeping track of and not making the mistake of just adding all of these constants together becomes kind of the crux of the method. So in this alternative approach, we'll kind of look at how we can do this a little bit more algebraically so that we're just worried about combining like terms and we don't necessarily have to keep track of the individual values. So the task at hand is to find integers s and t such that s times a plus t times b equals the greatest common divisor between a and b. Okay, for integers, again, a and b are integers. So the first task, of course, between those integers is to find the greatest common divisor. And then once we have that, then we've seen it as working backwards, working the Euclidean algorithm backwards, calling it the extended Euclidean algorithm, to find these values s and t. So let's look at this in another way. Let's study this example, GCD between, we'll say, 296 and 124. So we do have to carry out the Euclidean algorithm to actually find the GCD, and it's not just a matter of getting the GCD that's important, it's the process that we're going to need to still reference. So first thing we need to ask ourselves is, how many times does the smaller value go into the bigger value? And then what remainder does that leave? Well, I can see that that goes in twice. 2 times 124 is 148, and that means there's a remainder of 48, since 48 plus 48 equals 96. Okay, so now we know that the GCD between 296 and 124 is the same as that between 124 and 48. And so once again, I'm going to ask myself, how many times does 48 go into 124 and what remainder does it leave? Well, I can do it twice. I can't do it 3 times. 2 times will give me 96. And I believe that's going to give us a remainder of 28. Okay, so just going to check that. 124 minus 96, I always make a mistake here, is 28. Okay, again, the GCD between 124 and 48, its divisor, is the same as the GCD between the divisor and the remainder. So 48 is equal to some number of multiples of 28 plus a new remainder. Well, 28 only goes into 48 once, leaving a remainder of 20. And the GCD between 48 and 28 is the same as that between 28 and 20. 20 goes into 28 one time, leaves a remainder of 8. And now working on 20 and 8. Okay, 8 goes in twice, leaves a remainder of 4. And I'm just about done here. Now between 8 and 4, well, 4 goes into 8 2 times and leaves a remainder of 0. So my greatest common divisor is equal to 4. All right, now at this point, I know that 296 and 124 are my A and B. So what I'm going to do is I'm actually going to reference these values as A and B. And in fact, if you look at the first equation here, this one suggests that A is equal to 2 times B. Okay, so this is A, this is B. So we're going to actually, anywhere we see 296 and 124, we're going to represent those with A and B. Okay, so I actually get now an algebraic equation. And now it's going to be a little bit easier to manipulate because now I'm going to be working with A's and B's and I can focus on combining like terms. In the second equation, I have B is equal to 2 times 48 plus 28. Okay, now this is still where it's tempting to write this as b is equal to 124, which it is. But now I'm actually going to start with this second line, and instead of working backwards, we're going to continue working downwards until we get to the end. So b is equal to 2 times 48 plus 28. So what I'm going to do is I'm going to solve for the remainder in here. So if I subtract 2 times 48, I'll have 28 equals b minus 2 times 48. Now the key here is don't multiply them out, because now I have the ability to substitute. In this first equation right here, we're going to write that 48, again, solve for the remainder, is equal to a minus 2b. All right, so that's the setup, the initialization. The first two lines of the Euclidean algorithm give you a and b, because once again, 124 is the value of b. And that's all the substitutions that we can make with our quantities. All right. So then the second step is let's solve for the remainder in the first two lines. And now we're going to do forward substitution. So in other words, notice that 48 I can express in terms of a and b. Okay. So this means that 28 is equal to b minus 2 times the quantity a minus 2b. Ooh, we kind of like this because now it's simply algebra, and we get b, and we'll distribute the negative 2. We'll have negative 2a plus 4b. We'll now combine like terms, so this gives us 28 equals negative 2a plus, and we have 1b here, 4b, so we have 5b. Okay, so it's no different than using x and y. And so now we have what 28 equals. We've combined the first two steps. Well, now we need to move to the third line. Okay, so in the third line, if we now represent that in terms of its remainder, that's going to be 20 equals 48 minus 1 times 28. Okay, so we can already see where we're going to end up making substitutions. First of all, we see that 28 is equal to this line that we just wrote. And also, we note that 48 is equal to the original thing we wrote down. So once again, we just get to substitute out the two quantities, namely the dividend and the divisor both get to be written out in terms of a and b. Okay, so here we go. Let's get back at it. So 20, maybe I'll go ahead and write this down here. 20 is equal to 48, which is a minus 2b, minus 1 times 28, which is negative 2a plus 5b. And again, we're just going to combine like terms, so it just becomes algebra. We'll have a minus 2b, distribute the negative 1, we'll have plus 2a minus 5b. And this gives us, after we combine like terms, it gives us 3a minus 7b. Now, just as a quick check along the way, if I take 3 times my a value, 3 times 296, minus 7 times my b value, which is 124, I should ensure that I get 20, which I do. If I didn't get 20 when I carried out this operation on a and b, I know I made a mistake somewhere in my substitution. Well, guess what? Now it continues on, and now my previous two substitutions will take place. So notice that in this next line, we have 20 and 28. And I'm going to take just a moment here before we proceed with that next step just to highlight what substitutions we're making in each of these lines. So notice that here in this 20 line, we made substitutions for 28 and 48. In this next line, we're going to make substitutions for 20 and 28, and then 8 and 20. And that's really going to be our last substitution. We don't need to go on to this last line because that will already give us some combination of A and B equals 4, right? Because when we solve for 4 in this line here, we'll get 4 equals, and that's exactly what we're hunting for. So this just makes it a lot easier, I think, to keep things organized. So let's move to the next line. 8 is equal to 28 minus 1 times 20. And as we said before, we're going to substitute 28, which is equal to negative 2a plus 5b, 20, which is equal to 3a minus 7b. So doing this highlighting here helps us keep track of that neatly. And so I'm just going to carry this down here. And so we have 8 is equal to 28. Okay, 28 is equal to negative 2a plus 5b. So all I've done there is just replaced 28 with what it is equal to. Minus 1 times 20, well 20 is equal to 3a minus 7b. Okay, combine like terms, negative 2a plus 5b, distribute the negative 1. That gives me this quantity, and I get 8 is equal to negative 5a, combining like terms, plus 12b is equal to 8. Now, just to check my work once again, I can do negative 5 times 296, which is my value of a, plus 12 times 124, which is my value of b, and lo and behold, we get 8. So everything is good so far. Our last line now entails solving for 4 here. 4 is equal to 20 minus 2 times 28, 2 times 8, excuse me, which is a true statement. And so now I'm going to make my final substitutions. What am I going to substitute out? Well, the 20 and the 8 is what I'm going to substitute out. And I've highlighted that to make it evident. So I can just kind of go down now. So 4 is equal to 20. 20 is 3a minus 7b minus 2 times 8. 8 is negative 5a plus 12b. And this gives me 4 equals 3a minus 7b plus 10a minus 24b. And so if I combine like terms, I get 4 is equal to 13a minus 31b. In other words, now that we're done, this is the GCD between a and b. That is the GCD between a and b. So if I rearrange this, I can say that it's 13 times 296 minus 31 times 124 that gives me my GCD. So 13 is my value of S, and negative 31 is my value of T. That is a very algebraic way to go about doing this without having to worry too much about what it is that we're keeping track of, because we get to use substitutions, and then when we're combining like terms, we don't have to worry about accidentally combining things and multiplying things out that we weren't supposed to, because there's only so far we can go with having terms containing A and terms containing B. So to kind of recap, circle back to the top, the first thing we did is the first two lines gave us expressions for A and B. So anywhere we had a 296 or a 124, we put in an A and a B as appropriate. Once we had that, then we started in the second line, solved for the remainder, and then for 124 and 48, made substitutions. Actually, we already had 124 was B. Then for 48, we put in A minus 2B, got that first line, and now move to the third line in the Euclidean algorithm, solve for the remainder, substitute in our two previous 48 and 28, get a new expression, and now that gives us an expression for 20. So in this next line, when we write 8 equals 28 minus 1 times 20, we use the two previous substitutions, 28 and 20, to plug in there, got a new expression, then went to solve for the last line being the one before we get a zero remainder, because that's going to give us, that remainder is the GCD, and we're able to package it all together nicely. Now, here's the thing. This actually has the equation S times A plus T times B equals the GCD between A and B. It has infinitely many solutions. Okay, infinitely many. How can this have infinitely many? Well, all we're saying is that 13 and negative 31 are kind of the first two values that will do this. I mean, 13 is the smallest possible integer for S that we can have. Now we can certainly make them bigger or invert their signs. Here's how. So let me just point out in our equation 13 times 296 minus 31 times 124. One thing that I could do here, and this equals 4, I'm going to leave myself a little bit of space. And what we're going to do is we're going to perform a little add zero trick. Okay, so we can probably agree that if I add something and simultaneously subtract it, then those two quantities will cancel out. So let's recall that this value here is A, and this value here is B. Now the trick is to both add A times B and to subtract A times B. This right here still equals 0. I haven't changed the left-hand side of the equation. I don't need to do it to both sides because this just cancels out. But the power in doing this is I'll have 3 times 296 minus 31 times 124 plus A times B. Okay, so plus 296 times 124 minus 296 times 124. And that all equals 4. Again, these two terms still zero out. But if I think about the 296 and 124 as I have 296 124s and I have negative 296 124s, then I can actually appropriately add them as multiples to, I currently have 13 296s here. So if I rewrite 296 times 124 as 124 296s, and I write this as negative 296 124s, like this, then I can see that these are like terms right here. These two are like terms. If I have 124 296s and then 13 more 296s, that gives me 137 296s. And then here I have negative 31 124s. Here I have negative 296 124s. Negative 31 plus negative 296 is going to be, let's see, negative 327. Negative 327 124s. And I'm claiming that this still equals 4. Well, assuming I've combined like terms properly, 137 times 296 minus 327 times 124 indeed gives me 4, and this checks out. So I've just found a new coefficient here and a new coefficient here that will satisfy this equation. So if I look at the possible values for s and t, the ones that I came up with the extended Euclidean algorithm, are unique. I'll get 13 and negative 31. But I also came up with another pair here, 137 and negative 327. Now I could do the same thing again. I could again add 124 times 296 and subtract 296 times 124 and adjust these coefficients accordingly to produce another solution. So let me do that. 137 times 296 minus 327 times 124 plus 124 times 296 minus 296 times 124. Again, those are like terms and they add up to 0. So I haven't changed the equation any. But I can do the same thing once again. I have 137 296s. I have 124 more. 137 plus 124 gives me 261 296s. And then here I have negative 327 124s. Here I have negative 296 124. So in total I have negative 327 plus negative 296 is negative 623 124s. And I'm claiming that that should still equal 4. Let me check my work. 261 times 296 minus 623 times 124. Lo and behold, I get 4. So let's see if we can generalize our pattern here. So in general, because I know that with numerical values this could get a little trickier to keep track of. Let's say that we found, and I'll up here I'll also populate our new pair, and we can keep doing this indefinitely. If we have s times a plus t times b equals the GCD of a and b, then we said that one thing that we could do to generate another solution is to add a times b and subtract a times b. And that still equals the same quantity, the GCD between a and b, because let's recall that this right here is still equal to 0. Well, not only can I actually add a and b and subtract a and b, but I can do it as many times as I want. So here's what I'm going to do. I'm going to say, well, since I can do that as many times as I want, I don't just necessarily want to keep repeating these steps. I'm going to say that I could actually add k copies of a and b, but then I would have to subtract k copies of a and b. Okay, those still add up to 0, and k is just some integer. It can be any integer. I can do it negative 2 times, 3 times, 4 times, negative 5 times, negative 4 times. Doesn't matter. These two will always cancel out because KAB minus KAB is still 0. So I get to choose that k, and for this example, k was equal to 2 because we added AB and subtracted A and B here, and then we did it again. We did it twice. All right, so this is going to give us a nice general result. So let's write it like this. We have S times A, and we're almost at the punchline here, S times A plus T times B plus, and I'm just going to go ahead and write KBA, and over here I'll do minus KAB. So the way I'm going to think about this is I have KB copies of A, and here I have negative KA copies of B. Now again, all I've done is, because multiplication is commutative and associative, these two still cancel out and give me 0. Thus, the left-hand side still adds up to the GCD of A and B. Okay, now let's just combine like terms. Let's switch colors here. So here we have S copies of A. Here we have KB copies of A. So how many total copies of A do we have? Well, we have S plus KB more. So we have S plus KB copies of A. And then here we have T copies of B. Here we have negative KA copies of B. So combining like terms, we have T minus KA copies of B. And that will still ensure that we get the GCD between A and B. Okay, so what's the takeaway here? So to generate solutions, first find S and T by the extended Euclidean algorithm. So that's just our standard process that, depending on whether you like the forward substitution method here or the back substitution method, like in our last video, you can decide how you want to carry that out. To generate solutions, well, to generate additional solutions, notice that this solution right here really creates the unique solution for k equals 0. Okay, so this is for k equals 0, because you notice if k is 0, then you just get SA plus TB equals the GCD between A and B. And now to generate solutions, pick additional integers k and generate pairs. Okay, let's actually do this. We've already kind of created this ST table, but I'm going to create an KST table. And for our example up here, where we originally had 13a minus 31b equals 4, 13a minus 31b equals 4. Now remember, a and b are just 296 and 124. And this is our value of s. This was our value of t. Now this is when k is equal to 0. By default, you find the s and t for a k of 0, because again, it's just sa plus tb. And now I'll pick another value of k. So if I pick the value of k of 1, well, let's see. The s, this will actually be s plus kb, and this will be t plus k, t minus ka. Okay, that's that and that. So if k is 1, then I'll take s, which is 13, plus 1 times b. b is 124. If I take 13 plus 1 times 124, I get 137. And if I take t is negative 31, minus 1 times a, which is 296, I get negative 327. Now that's consistent with what we came up here. This was just for one iteration, k equals 1. And I can repeat this indefinitely. I can now do s plus kb, so 13, maybe I'll write that out up here. This is really just 13 plus k times 124 this here is negative 31 minus k times 296. So if I take 13 plus 2 times 124, I get 261. And then if I take negative 31 minus 2 times 296, I get negative 623. And let's just check our work up here. We got 261 and negative 623. Now the beauty of this is I could pick any value of k. There are infinitely many, and remember k is an integer, so k could actually be negative 1. Okay, if k is negative 1, then I'll have 13 plus negative 1 times 124. That will give me negative 111. And negative 31 minus negative 1 times 296 will give me 265. The reason I plug in a negative here is because in some cases you want the coefficient of, say, a to be positive, like we have for when k is positive, but we have certain circumstances where we might want the coefficient of a to be a negative, and that's going to involve subtracting 1 times the value of b. And so we'll go the opposite direction if we, say, do negative 1, negative 2 here, and we could find these values as well. This one will start to become more negative, this one will start to become more positive, because here we're subtracting a negative, we're adding, and here we're adding a negative, which is subtracting. So not only do we have control over those infinitely many solutions, but we can say the solutions are of the form S plus KB. Okay, so for our problem that was S plus KB and T minus KA. Okay, for our particular problem, that equals 13 plus, I'll write it as 124K, and negative 31 minus 296K. And this is how we would describe the infinitely many solutions where K can be any integer. So, pick additional integers K and generate pairs of the form S plus KB and T minus KA. S, T, A, and B are already given to us, and K we get to choose as a value to generate a brand new set of coefficients.